Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will continue to examine non-ideal ammeters and voltmeters. Okay, so recall from a while ago that we discussed how we were using ideal ammeters and voltmeters and how they can be wired into the circuit without affecting its properties. Okay, so we just assumed that we can use ammeters and voltmeters without affecting the circuit that we put them in. We said that ammeters need to drive current through the ammeter and therefore need to be wired in series with whatever element you find most interesting. Voltmeters need to be wired in parallel so that they can measure the potential difference across whatever circuit element we're interested in. So here's the problem, which is that these are ideal ammeters and voltmeters, and real ammeters and voltmeters will in fact affect the circuit a little bit. So what would the effective resistance of the instruments need to be in order to be ideal? So we can ask the question, what should the resistance of an ideal ammeter and what should the resistance of an ideal voltmeter be? Okay, and this will have different questions or different answers. Let's start with ammeters. So for an ideal ammeter, we want the ammeter to read exactly the same current that goes through R without affecting that current. As a result, for an ideal ammeter, we would want the resistance of the ammeter to be 0 ohms. Okay? Mathematically, why is that? Well, without an ammeter, the current is equal just to the EMF divided by the resistance of the resistor alone, R sub R. Okay? With the ammeter, the current would be the EMF divided by the resistance of the resistor plus whatever significant resistance from the ammeter would be. So it would reduce the current a little bit. So in order for the ammeter not to affect the resistor, ideally it's 0 ohms. In practice, we need it to be much less than the resistance of the resistor itself. So in order for I prime to be basically I, in practice we need the resistance of the ammeter to be much less than the resistance of the resistor. Notice that this means that real ammeters are going to have a small but non-zero resistance. Okay? This also means that real ammeters are breakable. They really are. If you put them in the wrong circuit, okay, you can drive way more current in them than they can handle because they have a small resistance. So you have to be a little bit careful about what your ammeters are rated for. It's much easier, as it turns out, to break an ammeter than it is to break a voltmeter, right? So what happens in practice with this real ammeter? Well, a real ammeter can be modeled as having its own little resistance of the ammeter, in series with the ammeter, with sort of an ideal ammeter. So this thing, a real ammeter, is basically the combination of an ideal ammeter plus a tiny little resistance. And as a result, what a real ammeter will do, if RA isn't much smaller than RR, is slightly increase our total and therefore decrease the potential drop across R and decrease the current through R. So I sub R will be measured to be too low. Okay, so it's going to affect both the potential difference across R and the current through R if that real ammeter does not have sufficiently small resistance, because this is what you will actually measure.